Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to your favorite Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our playlist Basic Electrical Engineering and Class 12th Physics in our subject Alternating Current Circuits we'll understand phasor representation, and in this second learning video after introductory part we'll explain mathematical base of phasor representation and how this phasor representation helps us to simplify mathematical manipulation among alternating quantities like summation, subtraction, multiplication or division. We'll understand two forms of phasor representation, rectangle form, polar form, and we'll use rectangle form for addition and subtraction and polar form for multiplication and division. So let's start this core understanding part of phasor representation. Phasor is a rotating vector whose scale length is equivalent to the magnitude of sinusoidal quantity, and its position with respect to horizontal reference represent T0 instantaneous magnitude of sinusoidal time varying alternating signal or phase angle of that signal, and this phasor rotates with an angular velocity in anticlockwise direction equivalent to angular frequency of sinusoidal signal, and during rotation the projection on vertical axis represent, if this scale length is equivalent to peak value of sinusoidal signal, then that representation is instantaneous magnitude of sinusoidal current, and if phasor is represented by respective RMS value, then projection of vertical axis proportionally represent instantaneous value of time varying sinusoidal alternating current. In exponential notation, phasor is represented by this mathematical expression where this represent magnitude of phasor. Presently we are treating amplitude or maximum value as amplitude of phasor, but in power calculation, since RMS value of alternating signal is more important, so we will take magnitude of phasor equivalent to its RMS value. This phi represent phase angle of sinusoidal quantity that relate T0 initial instantaneous magnitude of sinusoidal time varying alternating signal, and this omega is angular frequency multiplied by time in second become an angular measure argument, and this argument is a time varying parameter that represent rotation of phasor in anticlockwise direction with velocity equivalent to angular frequency in radian per second. If we have to represent a standard reference sinusoidal alternating voltage whose T0 instantaneous initial value is 0 and which is increasing in positive direction in a typical nonlinear sinusoidal manner, then phasor got its magnitude equivalent to amplitude or peak magnitude of sinusoidal signal and its phase angle being 0. So this phasor have initial T0 position along horizontal reference axis, and as per angular frequency with time phasor rotate in anti-clockwise direction, and as it rotate by 30 degree, its projection on vertical axis become half of amplitude, and that become instantaneous magnitude at that time instant. And if it make a quarter cycle, then projection on vertical axis become equivalent to amplitude of sinusoidal signal, and will have positive peak instantaneous value. Further rotation of phasor reduce instantaneous magnitude after half cycle instantaneous value as projection on vertical axis become 0, and after that voltage change its polarity, current change its direction, and our alternating signal instantaneous magnitude become negative, and at 3/4 of cycle this become peak negative, and further rotation reduce negative magnitude, and one complete cycle of rotating phasor represent as its projection on vertical axis time variation of this sinusoidal signal, and further rotation represent the same cyclic variation again and again. So we can say this waveform, this trigonometric mathematical equation, this exponent relation, and this line diagram all represent the same standard reference sinusoidal alternating voltage, and this representation by a line with rotation frozen at t equal to 0 position is called as phasor representation of sinusoidal quantity. If a sinusoidal time varying alternating signal starts from positive peak at t equal to 0 initial condition and would have a sinusoidal time varying alternating variation as shown here, then its t0 position on standard wave is corresponding to phase angle of 90 degree when the entire cycle is divided in 0 to 360 degree. So its phase angle become 90 degree, and when phasor of this sinusoidal alternating current is represented, the scale length is taken equivalent to peak magnitude or amplitude of voltage, and its t0 initial position with respect to horizontal reference is taken equivalent to its phase angle, and which is given 90 degree. And as per angular frequency of sinusoidal signal, this exponential relation represent that this Vm magnitude scaled length change its angle from horizontal reference, and this total exponential power at t equal to 0 90 degree represent t0 initial value of this phasor. Now time variation of instantaneous magnitude of this sinusoidal signal which starts from positive peak is of this nature, and it is represented as vertical component of this rotating vector, which is amplitude at t equal to 0, and at position 1 it become 86.6% of peak magnitude. After 60 degree rotation at this position 2, instantaneous magnitude become half of peak value. At time instant 3, instantaneous magnitude becomes 0. Now it change polarity, and at position 4, the corresponding vertical component of this phasor represent instantaneous magnitude of instant 4. At instant 5, it become negative peak. At 6, it reduce in negative direction, again change its polarity. At 7, it become half of positive peak, and at 8th position, as this rotating phasor has completed one rotation, one wave as vertical projection gets generated, and further rotation of this phasor repeat same alternating signal production. So this rotating vector position and this wave shape represent this mathematical trigonometric equation or exponential relation, and this is graphical presentation of phasor representation, and this is exponential notation of phasor representation. So in phasor representation, this represent the magnitude of sinusoidal quantity or scaled length of rotating vector or phasor. This represent phase angle of phasor or t0 instantaneous magnitude of time varying sinusoidal alternating signal, and this omega t represent rotating nature of phasor. If a sinusoidal signal starts from t0 instantaneous value 0, then its phasor will be represented by initial position at horizontal reference line and rotation in anti-clockwise direction with constant angular velocity equivalent to angular frequency. If instantaneous value at t equal to 0 correspond to positive peak, then this would be the initial position of phasor, and now it rotate in anti-clockwise direction, and as its projection on vertical axis produce one cycle of cyclic variation of that wave. And if a signal start from negative peak, then this would be the initial position of phasor, and rotation of phasor again represent time varying variation of that sinusoidal signal. If this sinusoidal signal starts from half of positive peak and increase in positive direction, then its phase angle is 30 degree, and corresponding to 30 degree phase difference, this would be the initial position of phasor. And as phasor rotate in anti-clockwise direction with angular velocity corresponding to angular frequency, its projection on vertical axis at time instant 1 represent instantaneous magnitude as positive peak. At instant 2, this position of phasor represent instantaneous magnitude equal to 0. At position 3, it would have negative peak. At time instant 4, it will cross 0 instantaneous magnitude and change polarity if it is voltage, and change direction if it is current. And at 5 position, it will have t0 initial condition, and one cyclic rotation of this phasor has represented one cycle of sinusoidal alternating variation as shown here as projection on vertical axis. So we can say phasor being a rotating vector can represent sinusoidal alternating signal. For the calculation of summation or difference of alternating quantities, they may be current or voltages, but all those alternating quantities should have the same frequency. We can use the concept of phasor representation, and here the sinusoidal alternating quantities are represented by respective phasors, and when these rotating vector are frozen at any time instant, these phasors become vector, and we can use vector simplification techniques, and resultant vector thus obtained at different time instants is found as rotating vector of same angular velocity. So we can prove that resultant rotating vector or phasor represent the summation of given alternating quantities. Here we have to find out sum of two current. One is I1, which is a standard reference sinusoidal current with initial t0 instantaneous value 0, shown by this black wave, and I1 sin omega t mathematical trigonometric expression. And the another current is I2 current, which leads I1 by an angle theta, as shown by this blue wave, and its mathematical expression is I2 sin omega t plus theta. Now these two sinusoidal quantities are represented by their respective phasor. I1 sin omega t is represented by a phasor of I1 length placed at horizontal reference with 0 angle to represent 0 phase position of this standard sine current. Another current is represented by a phasor of scaled length I2 and with an angle theta in anti-clockwise direction, showing that I2 current leads I1 by an angle theta. Now in a frozen state at t equal to 0, these rotating vector or phasor become a simple vector, and their vector summation can be obtained by parallelogram of forces, and that result is given by vector I as shown by this brown characteristic. And now in this diagram we can say the vertical component of these rotating vector represent instantaneous magnitude. I1 got instantaneous magnitude 0 at t equal to 0. I2 got this much amount of instantaneous magnitude, and this and 0 when summed gives this resultant instantaneous current as shown by vertical component of this brown I vector. Now after a certain time, these rotating vector I1 and I2 obtain a new position as shown in this 2 position. Since both I1 and I2 have the same angular velocity of rotation, as both current are of the same frequency, the relative phase difference between I1 and I2 remains the same. So neither the magnitude of I1 nor the magnitude of I2 nor the angle between the two had changed. So the resultant got the same magnitude and same relative angle with I1 as in position 1 from this parallelogram of forces principle, and this clearly indicate that this resultant vector shown by brown line is also a rotating vector, that too of same angular velocity or is phasor, and if its vertical axis projection is tested as sum of instantaneous magnitude of first and second, then we can say that summation of two alternating currents can be obtained by vector calculation using the concept of phasor. In this 2 position, the vertical component of this brown vector is sum of vertical component of I1 current, this magnitude, and this is vertical component of I2 current shown by this line, and the sum of 2 is resultant instantaneous current. So we can say sum of two phasor in frozen state obtained by simple vector calculation gives us resultant phasor for sum of two currents in this case. Now in place of this graphical approach, we can perform some easy mathematical analytical actions to get this resultant current for summation and difference, and for that we have to first understood how phasors are mathematically treated in rectangle and polar forms. In exponential notation, phasor is a complex quantity. This phasor representation contains not only its rotating nature, but it also have information of amplitude and phase angle of sinusoidal quantity. Now this concept of phasor given by C.P. Steinmetz is based on Euler identity and Euler relation relate exponential function to trigonometric function, and as per Euler relation, e raised to power eta theta is cos theta plus eta sin theta. Now in pure mathematics, this J notation is used as small I as eta, but in electric circuit we use small I as current. So just to avoid confusion and ambiguity, in place of eta small I, we will use the symbol small j. Now this letter j used in these relation in as power to exponential function or before this second number is a imaginary number, represented mathematically as square root of minus 1. Now on real number line, this j number is neither in between 0 and plus 1 nor between 0 and minus 1. It is nowhere on real number line. So we have a separate number line called as imaginary number line, and above this horizontal line imaginary numbers are plus j type and below that are minus j type. And in this notation, this e raised to power j theta represent a vector of unit magnitude making an angle theta with horizontal reference, and when we take its two resolve component, one along horizontal line we call it real line, then component is cos theta, and another at vertical line we call it imaginary line, the component is sin theta. Now if in place of theta we consider a time function omega t, then that vector will change its angular position from horizontal reference line and become a rotating vector, and such rotating vector become phasor. So e raised to power j omega t is a phasor representation which represent rotating nature of phasor, and its real component become cos omega t and imaginary component become sin omega t, and this sin omega t is used to express instantaneous magnitude of sinusoidal quantity. So the imaginary part of this phasor can represent instantaneous magnitude of sinusoidal quantity. So phasors which represent sinusoidal quantities are complex expressions, and such complex expression can be represented in phasor diagram. Here this e raised to power j omega t represent rotating nature of phasor, and since all sinusoidal quantities in concern with mathematical analysis possess the same angular frequency or angular velocity, this is a common term, and we are more interested in magnitude of phasor and its phase angle. And e raised to power j is a typical representation. To make it easy, we can say that phasor got a magnitude a and angle with horizontal reference theta as shown by this vector line position. A is scaled length of this phasor and theta is its angle from horizontal reference. Now this representation, magnitude angle form, is known as polar representation of phasor, and when its two resolve component is obtained, one along horizontal line a cos theta, another along vertical line a sin theta, then these two a cos theta, a sin theta component format is known as rectangle format. And here this j notation represent imaginary nature of this a sin theta number, and this line j line is known as imaginary line. So we can say in rectangle format phasor got two component, one is real component along horizontal line and second is imaginary component along vertical line, and this ax plus j ay representation is known as a rectangle representation, and this a angle theta representation is known as polar representation. When polar expression of phasor is resolved as two rectangle component a cos theta and a sin theta, then this multiplier j with vertical resolve component of phasor or ay represent imaginary part of complex phasor quantity. In our phasor concept, this multiplier j operator can rotate any phasor by 90 degree in anti-clockwise direction, as here we have one vector of magnitude 5 along horizontal reference line, and if we multiply this 5 with j operator, then it becomes j5, and with the same magnitude of 5 unit, this vector will rotate in anti-clockwise direction by 90 degree. If we make one more multiplication of j with j5, then it will become j square 5, and in mathematical sense j is square root of minus 1, so j square is a real number minus 1, and this j square 5 become minus 5, and minus 5 is just an opposite vector of 5 with same magnitude but just opposite direction. So this would be position of minus 5, and we can correlate that when j5 is multiplied by j as j square 5, this j5 vector get rotated by 90 degree in anti-clockwise direction and got this position. If we make one more multiplication to this minus 5 with j, then it will become minus j5 and will got again 90 degree shifted position here at this position. So we can say to top of this horizontal line we have plus j imaginary numbers, and to lower side of it we have minus j numbers. So j got a separate number dimensions perpendicular to our real line axis, and now in graphical plot any phasor of magnitude a and angle theta can be resolved as horizontal or real component a cos theta or ax and vertical or imaginary component a sin theta or ay with j notation. And for us, j is a complex multiplier operator which can rotate a vector or phasor by 90 degree in anticlockwise direction without change of magnitude. Here a e raised to power j theta or a magnitude and angle theta is polar form of phasor, and ax plus j ay is rectangle form of the same phasor. Here ax is resolved component of a phasor along horizontal real axis and it is a cos theta or ax, whereas this ay is vertical resolved component of phasor a sin theta. In our electrical engineering, we call this real part of phasor a as in phase or active component of phasor, whereas this vertical component with multiplication of j associated with it is known as imaginary part of phasor A, and it is also known as quadrature or reactive component. So ax is real in phase active component and ay is quadrature imaginary or reactive component. The expression a e raised to power j theta, which is often simplified and written in form a angle theta, is polar form of phasor expression, and here a represent the magnitude of phasor vector or magnitude of sinusoidal quantity, and theta is inclination or angle in anticlockwise direction from horizontal reference as shown here, represent the phase angle of phasor. Now from horizontal reference, anticlockwise angles are taken as positive angle, and if the same angle is in place of in anticlockwise, top position is in downside clockwise direction from horizontal reference, then such angular expression become negative, and such phasor is represented as a e raised to power j minus theta or with a magnitude angle minus theta. If in one case we know two Cartesian coordinate or rectangle component of a phasor as ax and ay, then we can find out the magnitude of phasor in polar form a by simple Pythagoras calculation, as in this right angle triangle, base is ax, perpendicular is ay, and hypotenuse a is Pythagoras calculation of square root of ax square plus ay square, and out of phasor magnitude a, its horizontal component ax, its vertical component ay. If any two is known, we can find out the third one. Similarly, the angle which phasor makes with horizontal line theta can be obtained as tan theta is perpendicular upon base ay upon ax. So we have a relation between magnitude a angle theta, horizontal component ax, vertical component ay, and from these two relations, if out of the four a, theta, ax and ay, any two is known to us, we can find out other two. Two complex phasor quantities are called conjugate of each other in polar form if they have same magnitude and same angle from horizontal reference, but one angle is in anti-clockwise direction, positive angle, and second angle is in clockwise direction, negative angle. So two phasors are called conjugate of each other if from origin they have same scaled length, so they have same magnitude and they have same amount of angle from horizontal line, but one in positive anti-clockwise direction and another in negative clockwise direction. So with same magnitude, same angle, but one angle positive, second angle negative, pair is known as conjugate pair of phasors. In rectangle form, two phasors will be called as conjugate if they have same horizontal or real axis component and same vertical axis or imaginary component, but the sign of imaginary component in one phasor is positive and in another phasor it is negative. So here these two phasors are conjugate of each other as they have the same amount of real component and same amount of vertical component, but one vertical component is to upside in positive j direction and another is to bottom side minus j direction. When we'll take sum or difference of two conjugate phasors, then in sum the imaginary part get vanished and in sum we get only the real component, whereas for difference calculation, the real component get cancel out and will get only imaginary or reactive component. We hope this beautiful learning video has explained every mathematical aspect of phasor representation, and now you understand both polar form of phasor representation and a rectangle form of phasor representation, and soon we'll discover that for summation and difference it is the rectangle form which is used in analysis, and for multiplication and division we will use polar form, and it is very easy to convert rectangle phasor form into polar phasor form or vice versa. In next video of phasor representation we have explained this fact. Our other learning video of the same playlist are equally useful. You can use them in your studies or refer them to your friends. And if you need exam centric notes or online doubt clearing classes from this channel, do join our YouTube membership. Happy learning. Have a nice time. Thank you very much.